Great pleasure to introduce Yoh Tanimoto from the University of Rome to Vergata, who will speak on free products and AQFT.
So it's my pleasure to give a talk here. I would like to do some recent work on some free product in algebraic QFT. So it's about net of fundamental algebras. So this free product is free product of fundamental algebras. So you operate algebras. I think anyway. And so this concept might look with contradicted at the beginning, because this free product is something very non-commutative. While in AQFT we consider local algebra, so some family of commuting operator algebras. And indeed, so that was how this research started. By the way, this is joint work with Roberto and Yoshimichi Ueda. So, in the sense that it's sometimes in the sense that the free product, so we have a family of fundamental algebras. So here we have an index set, okay? It may be finite or infinite. So there is family of fundamental algebras associated accompanied with a state vector. For simplicity, I assume that this is cyclical separating. Okay. They are defined on, so each of these families is defined on the Hilbert space HK. And the free product, I will give the definition, formal definition later, but this something is the free product. So they are fundamental algebras. Understood. Free product. M. So this is actually associated with a distinct state, and also that sometimes I denote it with star. So all this stuff. Is something that is a fundamental algebra, which is generated by some faithful image of these families, some family of fundamental algebras, but each of these images does not commute with each other, in the sense that MK1 and MK2 do not commute. I will tell you how exactly this is constructed. So this is one side of contrast. And on the other hand, in AQFT, or especially in conformal or Moebius covariant net, so we consider a family of commuting fundamental algebras. If you attended some lecture courses already, is so you have here you have a family of Neumann algebras. So this is which is parameterized by intervals or in the circle, and this is local in the sense that if actually there is some representation here on omega. Anyway, so this is a very commuting stuff in the sense that if you have disjoint intervals on circle, if you have two disjoint intervals, then and the corresponding fundamental algebra should commute. So in AQFT, we are interested in some such family of fundamental algebras. So there's some contrast between these. Actually, even if there's no relation between these index sets here and this k is just general, and this other geometric meaning, but contrast yet. And indeed, why we started this research is actually we wanted to find a certain counter example to the following notion. Sorry, but I have away the eraser. I still don't need it.
So the red thing on the lectern there.
Yeah.
Next
No,
to
no. Ah, okay. I see. Yes. So Moebius covariant net, because this is a huge family, so you have all the intervals connected, but all the intervals in S1, so this is a huge family of fundamental algebras. But this family can be reconstructed from just an inclusion of two fundamental algebras. This is called half-cycle. This is the definition. So it's after the modular inclusion. So here you have just two fundamental algebras, one inside the other. So this is always a state vector. And such that so the modular automorphism group is of M with respect to this state. Preserves this subalgebra, but only for positive parameters. So this is called half-sided inclusion with respect to the modular automorphism. This is called a half-sided modular inclusion. And if additionally we have additional condition that this is called the standard half-sided modular inclusion. It's cyclic for both n and the relative component. And so another thing that so as you know, Moebius covariant net is realization of quantum field theory in low dimension, one higher component one of 1+1 quantum field theory. And that information is already contained in here. If there's a one-to-one correspondence between actually actually the other additional condition, but I'm not going to explain. Stronger disease. And indeed, so this M and N and N will be in this correspondence. There will be some of these algebras in some of these families. And from the modular data, you can recover all the structure. So the point is that this is standard. So this vector omega should be cyclic for n, but also for the relative constant. But even if it is not standard, you can still do the following. So even if you can construct a Moebius covariant net on this subspace, just by restricting everything to this subspace. It's relatively easy to construct some half-sided modular inclusion. So there are natural questions whether if you have a half-sided modular inclusion, then what can you say about the relative content? Because until now, before this work, so nothing was known. So it could be that that any half-sided modular inclusion, it has non-trivial relative content, and that would have been very interesting because then you get some quantum field theory. But actually, we found a counterexample using this free product technique. So this is the first of our result. So it's all so this is the first question, and the rest we are very. And I'm going to construct this using the half and free product. And actually, we need an infinite free product. So the free product of infinite copies of the same half-sided modular inclusion. On this. So in the course I will tell you also we can construct using the free product something which is close to AQFT setting, sort of net. And the second question is not necessarily Moebius covariant. And so this is the second question. So we still don't have a definite answer. So
Also, why can't you just take n equal to m? Which part of that, which property fails if n is equal to m?
And then the n is equal to n, and the relative commutant is trivial.
Yeah.
Is that your
Yeah, why
question?
don't you just take n equal to m together to the relative commutant?
If, so in that case, so for example, you just don't get any net because in this standard situation, so you can get the modular automorphism group for n and m and also for the relative commutant. So this all of three generates representation of the Moebius group. But if n and n are just the same, you don't get any.
So I mean, for half-sided modular inclusion, is it required that only for positive t? Is it only for positive t, or you can
Only for no only for the formal definition you can take only for positive t. But if they are just same, then you.
I'm just wondering if that's considered, if that would be considered a half-sided modular inclusion. I mean, it doesn't really matter, I guess. It's just a trivial case, I guess.
In that case, we are not interested.
If n is equal to m, is that considered a half-sided? Is that considered a half-sided? Is that?
You could say that, but we are not interested in that.
Okay. Sorry.
No.
It's trivial. I'm just curious.
So. I will tell you, maybe we can construct something using just finite free product. So let's start to find this free product, one of these. So as I said, the free product we need a family, so index set k. This family of fundamental algebras and states on page k. So nowadays you can also characterize the so-called free product of this family, but it is also it can be also constructed in a very concrete way, and I'm going to tell you this concrete version. So here you need the first the Hilbert space one dimension less than this HK. This free product on the algebra is going to be constructed on a huge Hilbert space, which has this one-dimensional part plus so here you have tensor product of finite tensor product of this small, just as one dimension, smaller Hilbert space, where all these indexes are different when you compare the one from one. For example, if in general, if you compare 1 and 2, they must be different. Or in general, if you compare j and j plus 1, all these are k must be at least k must contain at least 2 elements. So this is the Hilbert space where the free product is going to construct. And the point is that so H for any k, you can easily write this k as a tensor product of this hk without this circle plus times something. No, sorry. You can write this as a tensor product because this is here you have all the ordering alternating ordering of index set. So if you take k, you can find some sequence which starts with k, and adding this part or some other part, you can identify the sequence with this part, the left part, with the full Hilbert space. And so here, the original von Neumann algebra acts, and we write this by the left action. So finally, so this we take the von Neumann algebra generated by these images of these actions, and so this is the free product of this family. And they are the distinguished vector omega. So this is the one-dimensional part. So we consider this pair as the free product. And because so here we have a vector and the distinguished state. I call it. So this has a particular property because if it xk, I take an element from mk, and if I take an element here, and I subtract the identity part with respect to the state, I subtract this identity part. And so this distinguished vector has the following property. So omega if I put here product of this element with circle, this is always 0. So sorry. So K1, K2, and always Kj. Because they are here that this xk with circle, they act as either as some. It takes this subspace to another direct sum component with this k plus 1 part on the first. So if you put everything on this state, so this is always diagonal from diagonal with orthogonal to this omega vector. So you get just simple computation. And with this property, you can also prove the following. So if we take the modular automorphism group of mk with respect to this state, and you can compute the modular automorphism group of this the free product algebra in the following sense that so in this sense, modular auto of this with respect to omega, if you compose it with this case element also with inclusion, and then you get just first you apply modular auto. So that is the commute or the actions of the modular automorphic group of any case carried through the free product. The free product from the algebra. So this is why it's useful in considering the half-sided modular inclusion, for example. Namely, so in this section I take some index set which is infinite, just any infinite, countable or uncountable, it doesn't matter. No, sorry. Here I need actually a copy. So I fix just a single half-sided modular inclusion, as you can see here, and I take infinitely many copies of the same thing. And then I take the half-sided modular inclusion. Sorry, the free product. So if this index set is infinite, then we can see the following. So in this setting, so the n and m are the same. The free product of the same thing, and then the first thing is that this pair is again a half-sided modular inclusion, and as I said, if this is index and then infinite, then derivative is on campus. It's true. On the proof, right, the following. Actually, the first part is very easy because, as I said, the modular automorphism is very easy determined. So, by the way, the proof is done by the KMS condition, which is easy because for any finite product of for any product finite in many elements, you can just get the product of analytic function, which comes from the KMS condition of the original function.
So the original one is any is a specific one, or is any n0 and n0 is which one is that? The original one you start with?
It's half actually.
N0 inside M0 is that a specific half-sided marginal equation, or is any?
Don't have. Sorry. There's one condition that. No. So this works like this. So it should be. It could be they and they might could be the same, but in this case the second statement will be trivial. But any half-sided modular equation would be okay. Anyway, the proof of the first part is trivial. Just by the proof. Right? Because we know that n is generated by the image of nk, and we know the action on the modular automorphism group. So just we can write it in 2 lines, and you get this inclusion definition of half-sided modular inclusion from the half-sided modular inclusion of the original smaller in the case. And the second part is actually it's more complicated, and in general. It's really difficult to determine the relative commutant of free product inclusion, free product from the algebras. There's also some developed techniques, but the techniques apply if you have conditional expectation from m to n, and the situation of half-sided modular inclusion is almost opposite. We are interested in the cases where the index is infinite, so probably no expectation. So in this case, in general, it's difficult. And the interesting point is the following. So we have actually, this triviality of the relative commutant holds for any non-trivial subalgebra n. That so let's say if non-trivial in the sense that if it is not just one-dimensional, if more than 2-dimensional, non-trivial. And then in the sense of output. And then you get this result. And here, so the relative constant is not true. This depends heavily on the assumption that the index set is infinite. So yes, because this is the proof of lemma. This is the core of the proof actually. So I take something from the relative commutant. So I just want to say that here I'm not using any structure half-sided modular equation. It's a result about free product. I take something from a relative commutant, and I take something from this subalgebra. And again, I subtract the identity part. So the task is I have to show that the relative constant is trivial, but I subtracted this identity part so that all I have to prove is that this x0 part, x circle part is 0 actually. And if I take this subtracted part, then I can prove the following. So I take subset. Just an arbitrary finite subset. And some other index from the complement. And of course this is possible because k is a infinite. No. Plane. So lambda. Sorry. I forgot to say that. If I take a subset of the index, then there is conditional expectation. To the subalgebra, which is generated by the MKs with indexing containing this. And then what I'm going to say is what I get is first I subtracted this identity part, so you get this. You apply first this element to omega and this A with different, so they are disjoint index set. So you get orthogonal vectors. So this is easy to find this freeness. Of the free product. And then the proof is that, so I have to prove that x is 0, and x is in the relative commutant, and A is in the small algebra. Image of A is always in the small algebra. So this and they commute. Sorry. I need to try. I will do it maybe later. This commute, because x is in the relative commutant. And we can write this in a way that I think I should in the following way. So from this relative constant, you compute just a bit, and you get that this is equal to And I take some element from the analytic. Maybe the signs are wrong, but it's not important. So, as I said, that these vectors are orthogonal to each other. So you get the following estimate. So you can estimate this vector, but actually this the norm of this is equal to, it's not the estimate. You get the equality, and this you get the equality, and this is smaller than something like the difference between something like this, and sorry. You can get this kind of estimate. So here I take the limit where, so the point is that you do this estimate, and so finally you get something which does not depend on k, index k, which is outside this subset. So I can take this limit, then this converges to the x0, so this particle to 0. Sorry, not in the norm. I have applied this. And then this it strongly converges, so I get 0. And while so B is just an arbitrary element, but I can take some analytic element from with respect to M. So this is how I get from this here to this estimate. And then so this will be almost so the b times omega 0 can be arbitrarily close to a times omega because it is cyclic. So this must be, so this goes to 0. And if so this smaller algebra is non-trivial, then I can take a non-trivial element A0. So this part should be non-zero. And if the right hand side goes to 0, then this part should be 0. So this yes. So it's almost algebraic computation. So as you saw in the proof, that it is important that you can take this trick. So you take any arbitrary finite set, and then you have some always something in the complement. So that's why this trick works. But finally, I'm going to but you can do similar thing. So I just tell you one thing. So the point was, so if so this theorem holds when the index set is infinite, but if it is finite, so it's finite, then then there is just inclusion. It's not half-sided modular. Just inclusion from the algebra such that the free product inclusion is non-trivial, and this is constructed indeed. This is proved indeed using some technique from Moebius covariant, because in the sense that in Moebius covariant net you can also consider some additional condition, which is called the trace class property. So Moebius covariant net is acted on by the Moebius group, but in particular rotation, and if this exponential of this analytic continuation of this rotation is trace class, then you get some local, some inclusion of local algebra which is split. So there's some intermediate type 1 factor. And in this case, so for such so split inclusion, I apply the split inclusion here, and if I take a finite product, and then I get a free product which whose relative constant is trivial, and I really use the technique of AQFT, and this heavily depend on the result of some just because don't know. It's interesting because this also again is such an example where you can determine the relative constant is rare. This can be proved using the AQFT. So I think and we are also working on constructing something not on the circle but in higher dimension. It's that